Hi, here is Peter Zeno-Korondi, and I would like to present my capstone project for the Advanced Data Science IBM course. The title of my project is X-Rotor, and the goal of the project is to make a classifier for identifying if a rotor design is good or bad. So imagine that you would like to build an electrical aircraft, and for that you will need a quite good rotor design because the battery is pretty much limiting your electrical power, so you need a very efficient rotor design. Now, evaluating the performance of rotor design is quite expensive. You have to either do wind tunnel test or you have to make some expensive CFD simulations. So it would be smart if you have just simply a very fast to evaluate model which can determine if your rotor design will perform efficiently or not. So we will say that our rotor design is performing efficiently if its efficiency is higher than 70%. And we will say that this is good. And if the efficiency is below this 70%, then we will say the rotor design is bad. So let's see what kind of data set do we have. So we have a data set of 20,000 rotor designs, and each entry of rotor design contains 8 design feature and 2 performance feature. So all in all, we have 10 features for each design, and the task is to build a model which takes the 8 design feature and outputs one output feature, which is the ratio between the thrust and the power, so the efficiency, and that is further transformed into a good-bad binary class. Now let's evaluate the quality of our dataset. So we have 20,000 entries, but unfortunately in some rows we are missing the performance features, and we have to filter out those rows because we weren't able to use to train our model. So after doing this, we will end up with 16,000 rows approximately, and basically we had to cut out 70% of the data. And after this we have clean data and we can really use for the model building. So let's explore a little bit our raw data. So if we plot all the correlation map of all the features, we can easily notice that the thrust and the power are pretty much correlated. So it is quite obvious that if we would like to generate more thrust, for that we will need more power. Now we can draw other conclusions that if we rotate more the rotor, of course we will have more power. For that we need more power, and we will end up with more thrust. And also if we go faster, that will reduce our power and will reduce our thrust. So this is coming from the aerodynamics, and these are all expected phenomena. Unfortunately, for the design features, we cannot notice any strong correlation, and of course that is not so good because we would like to somehow reuse our problem, and we would like to know how do we have to combine our design features to end up with a good design. Now, the final goal of the project is to really classify if a rotor design is good or bad. So for that, we have to calculate the efficiency. And the efficiency is just the simple ratio between the thrust and the power. So we calculate this, we can add this to the data set as a new feature, and then we have to create our classification labels if it's good or bad. So we simply add a 0 if it's bad and the 1 if it's good. And this we also append to our data set. After this, we can plot the performance features, and we can see that even though the data is cleaned, we have still some problem with the actual values, because for example, if we take the efficiency plot, we can see that we have some efficiency which are above 1, and that is problematic because obviously we cannot have a better efficiency than 1. That would be like generating energy from nothing. So we have to filter out these unphysical values. Okay, so we identify our outliers with one class SVM function of sklearn, and with this we can really filter out all the values which are non-physical. And if we take a look at our pair plots again, then we can see that the efficiency is always below 1, and that is good. So we can move on to build our model. So to build our models, we have to normalize our design features first, because that will enhance the performance of our model training. So we use the min-max scalar of sklearn, and that is a very simple method. And with that, we can really fit and transform our design features to a normalized values. After this, we will also split our data set to training and test data sets, so we will able to validate our model at the end. So let's see our models. So we would like to build a binary classifier. So first we can start with a logistic regression with the sklearn library from the sklearn library, and to evaluate the accuracy of this model, we will use the accuracy metric and the F1 score from sklearn library as well. So after training the logistic regression, we can see that the accuracy is not so good, it's 0.77, and the F1 score is even worse, which is 0.3. So we can state that this logistic regression was not really working well, and we have to build a better model. Okay, so instead of the logistic regression of sklearn, we can build a deep neural network with the TensorFlow, and hopefully that will result in a better model. So we will use 2 hidden layers, and each layer will have 64 units, and we will use this ReLU activation for each layer, except for the output layer, where we will use the sigmoid, so we can have the binary classifier. To train our deep neural network, we will use binary cross entropy and binary accuracy for the metrics, and we will use the ADAM optimizer. So all in all, this will result in approximately 5,000 parameters, and we will train that with throughout 30 epochs, and in each, and the batch size will be 64, and that will be quite quickly converged to our solution. The solution of the model is quite good. With the accuracy we reach like 0.94, and the F1 score is also 0.85. So this clearly states that this deep neural network is much better than the logistic regression of sklearn, and the high values of accuracy and F1 score of the deep neural net model indicates that we can use this for further development. Now, after having a good model, we would like to complete our data set. So we can evaluate all the designs in the dataset. We can complete the missing performance evaluation, the missing classification, and with this we can have 20,000 design and their evaluation if they are good or bad rotor designs. Out of this 20,000, we find out that we have like 3,500 good designs. So all of them can be considered for further development, further investigations, and later on, if we have a rotor design which we would like to explore, which we would like to test. Before testing, we can evaluate this rotor design with our model, and then we can decide in advance without spending any time in the wind tunnel laboratory or spending many hours and time on running expensive CFD simulation. We can evaluate if that design will perform good or bad with a very cheap function evaluation. So let's explore the correlation map of the good rotor designs a little bit. So from this correlation map, we can basically extract two quite important information. One of them is that if we would like to have a rotor which spins very fast when the RPM is high, when the rotational velocity is high, that will require low twist angles, because the twist angle will otherwise, if the twist angle is big, then there will be too big drag on the rotor blade, as basically the high twist angled rotor blade will make an obstacle in the air, and that will cause a lot of vortices after the blade. The other conclusion which we can say that if we would like to go faster, we need faster spinning rotor. So that is also quite obvious that. Okay, so to conclude our project, we are quite happy because we were able to train a deep neural network model which is quite accurate and quite good to do performance prediction. Even it's only a binary classification, the model performs quite good and can be useful for further development of a rotor. Now we also learned that the off-shelf logistic regression of sklearn is not so good, and deep neural network models are outperforming them, even though we used only 2 layers and a few units. So at the end, we are happy with the project. We achieved what we wanted, and thank you for the attention. Bye.